Hi everyone, thank you for listening to this talk today. I'm Chengquan from University of Science and Technology of China. Today, I would like to introduce our work, LitePred, Transferable and Scalable Latency Prediction for Hardware-Aware Neural Architecture Research. As we all know, DNN models are widely used in today's mobile and edge applications, such as face recognition, speech recognition, and AR/VR. To meet people's requirements of these apps, deployed DNN models need to satisfy efficiency constraints. To design such model with both high accuracy and lower inference latency on diverse edge devices, inference latency has become a crucial design metric during the model design process, such as hardware-aware NAS. Hardware-aware NAS has proven to be successful in designing affordable DNN models for edge platforms. It searched a large number of models and only consider models within the latency constraints. By doing this, NAS can search a model with both high accuracy and low efficiency on target device. Then, the question naturally arises: how to get the inference latency of DNN models on various edge devices? There are thousands of edge devices and various inference frameworks, and the NAS process will explore millions of models. So, on-device measurements is expensive and impractical. There are three types of related works. The flops-based method, using flops as a design metric, but flops doesn't reflect the real on-device latency. As we all know, two models with the same flops can have very different latency. The operator-level-based method, they simply sum up all the operators' latency as their model latency. And the latest work considers inference engine optimization that there is operator fusion at the inference stage. For example, Con2D and ReLU, two operators, are usually fused to one to make the inference efficient. They call the fused operator kernel. And they sum up all the kernel's latency and as model latency. We follow this way and take the sum of kernel latency as the model latency. The model level-based method leverages GCI models to learn the graph optimization and predict the whole model latency, but it is hard to generate to unseen devices or unseen models. All these methods need expensive rebuilding costs for new platforms. So we propose LitePred. The key idea of LitePred is that identify the most similar pre-existing latency predictors for each kernel on new platform, and then we just fine-tune them with just a few adaptation samples to achieve high prediction accuracy. This makes LitePred a cost-effective solution for predicting latency, eliminating the bottleneck in hardware-aware NAS. As the figure shows, the first step of LitePred is building basic kernel-level predictor from scratch and adding them to the knowledge pool. Then, when new platform comes, we perform similarity detection to identify the most similar latency predictor for each kernel. When we get the similar device predictor, we fine-tune it with just a few adaptation data over the target device. In this way, we can generalize to unseen devices and unseen models with minimal adaptation cost. To build our predictor, we face two technical challenges. First, each kernel configuration displays a multidimensional distribution, especially latency-dominant kernels. For example, as the picture shows, under different setting of HW, in channels and out channels exhibit different distributions. This makes the previous methods ineffective due to the auto-distribution problem. For example, adaptive stable sampling with performing independent sampling per dimension will introduce a large number of useless training data, resulting in low accuracy. This brings challenge in collecting high-quality training data aligned with the multidimensional distribution. Besides, since most platforms are black box, it's challenging to detect the most similar device for target device. To solve the first challenge, we propose our first key technology, efficient VE data sampler. VE is a type of generative network. It is mainly composed of two parts: the encoder encoding the input data into a lower dimensional latent space, and the decoder extracting the input data from the latent space. To train our VE model, the first step is collecting data from the NAS space, but it's not trivial. Since many latency-dominant kernels have low frequencies, we perform data normalization on HW in channels and out channels of these kernels. To train our VE model, we use two loss functions, MSE loss between the input distribution and the encoder output distribution, and the KR loss between the encoder output and the standard normal distribution. After the tuning process, the decoder is able to map the latency space back to the original kernel configuration distribution. When using VE model, we just pick up its decoder and sample some vectors from multivariate Gaussian distribution and pass them to the decoder. Then the decoder will generate data aligned with the space distribution. The next step is using this generated tuning data to tune our latency predictor. The latency predictor model is a 16-layer MRP network with only about 1 million parameters. We use configurations that the VE model produced plus flops and parameters of this configuration as input features and the corresponding inference latency as a label. Our tuning goal is to minimize the MIP loss between the predicted and actual latency values. We evaluated the performance using the plus or minus 10% metric, which calculates the percentage of our kernels with predicted latency within a plus or minus 10% margin of error. Under the same sampling budget of 10K data points, our VE data sampler achieved much higher prediction accuracy than the sawtooth method. But it still needs a large cost for profiling kernel latency. There are two key observations of us. As the figure shows, we measure latency of count-2D operators on various mobile CPUs, fix the same inference framework, and we fix the CPU using the different framework. We found that, as the left shows, fixing the inference engine, the latency exhibit the same delta case pattern, and fix the mobile CPU, there still exist frameworks exhibit similar patterns. This is primarily because some critical optimization techniques are commonly applied across these frameworks. So this gives us insights to train latency predictors to well-learn the latency patterns for a specific platform, and then transferring the shared common knowledge to a new platform. This is also the core principle of LitePred. Thus, we can limit the need for costly rebuilding process. So, how to identify the most similar predictor for a new platform? Since most other platforms are black box, we use latency distribution-based method to perform similarity detection, which means if the latency of two platforms plays a similar distribution, we consider they are similar platforms. We first design a few representative configurations. These configurations collected in two ways. First, we sampled in the search space to reflect the underlying distribution, and others are designed to capture the latency patterns, which reflect the on-device optimizations. We design second type configuration by fixing all dimensions except one, and performing fine-grained data sampling on that dimension. Then, we measure actual latency under the new platform and predict the latency of this configuration for each predictor in our knowledge pool. We calculate the KR divergence of measured latency and predicted latency, and we selected the predictors with minimal KR divergence as the most similar predictor. We perform this deduction to major kernels of DNN models, such as count-2D and count-2D operators. Then, we just fine-tune these selected predictors using the sample data by VE model, and updating their weights to improve accuracy on the new platform. We conduct our experiments on platforms with different hardware and CPU frequency, and inference framework and data processing, totally 85 platforms. And we use sampled models from 5 widely used CN and 1 with transformer NAS search space, more than 1 million model and latency pairs as our datasets. We achieve an average of 99.3% transfer accuracy, and 87% models are within plus or minus 5% error, and the adaptation cost is only 0.05 to 1.73 hours on same species. Compared to the sawtooth methods, we achieve up to 5.3% higher prediction accuracy with a significant 50 times profiling cost reduction. We evaluated the effectiveness of our similarity detection techniques. Fine-tuned from a similar device achieve higher prediction accuracy with less training data. Our method can effectively identify the most similar predictors for the target platform. Thus, when achieving a seamless accuracy, our detected predictor require 2.5 times less adapted data. By integrating LitePred into FA search method, we achieve up to 4.4% accuracy compared to the mobile nets across the various ad platforms. Thank you so much, and I'm happy to take any questions.